So in this lecture, we're going to practice using Fischer projections a bit with the goal of eventually getting used to these enough to where we can convert back and forth between Fischer projections and bound line structures. What I want to start with is actually, it's always helpful. It's good and it's healthy. Sorry, I've lost my screen. And the delay is ridiculous. Okay, there we go. Okay. So we've got our screen in front of us now. What I like to do is, whenever we can, I like to start with something from the literature. This is a recent article from ACS Catalysis, which is a nice journal. And what they're showing is what I have here is the graphical abstract. Now, in the graphical abstract, you see a bunch of fancy colors, but I hope you also notice that we have several Fischer projections. This is an interesting paper where they are engineering some enzymes to do some different organic chemistry than what we usually see. In particular, these enzymes are trying to flip a stereocenter of a common sugar. So there's one stereocenter as indicated by the cross or intersection of this Fischer projection. We're going to flip that into a different what we call configuration, or flipping it from an R to an S and S to an R. Let's see if we can figure out from what we talked about last time what the R and S configuration is in the original molecule, which is fructose or fructose, and then into tagatose. So if we redraw the bond line the Newman, not the bond line, if we redraw it as the Fischer projection, goodness. Okay, they actually draw this carbonyl as kind of coming off of the Fischer projection as a separate non-stereocenter kind of piece of the Fischer projection, and carbohydrate chemists like to do that. We'll give them a pass this time. But anyway, so we have kind of drawing this molecule, and I'm starting with, I'll start with fructose. Okay, so here is fructose, and it's labeled as the D enantiomer. That D label, the dextrorotatory label, is not super important to us at this juncture. Rather, I just want us to do some practical applications of using Fischer projections, because one thing I struggled with as a student, I'm just reproducing the tagatose here, is when I was an organic chemistry student in my whatever year of college that was, I struggled to understand why these things were so important. I really just wanted to make some bonds, break some bonds, that sort of thing, which that certainly is fun. But let's go ahead and use these as they're meant to be used. So what we have here is, did I pick a difficult stereocenter? That is, I want to focus on these stereocenters. They're the stereocenters that are sort of flipping between these two structures. Well, if we prioritize, we've got 1 and we've got 4. Got 1 and we've got 4. 4 is on the horizontal, so we're going to have to do some switching once we effectively prioritize these carbons. So I have a carbon here. I'm going to do a triangle and a circle. Now the priorities should actually be the same. So if you go kind of meandering through from the star stereocenter, we go to carbon, which ties with a carbon down. So carbon circle and carbon triangle tie. Moving on to the next highest priority element, we have an oxygen, and we have an oxygen. So there's a tie there. All right, so we have to kind of look on to the second highest priority element. That would be a carbon and a carbon. So those are the second highest priority elements. Now between those two carbons, even though they look the same, and the third highest priority at triangle and circle is the same at hydrogen, we can then see the difference. We have to treat the circle carbon as being attached to two oxygens. One of them is not real, we call it a virtual oxygen, but because it's double bonded to an oxygen, we assume it's attached to two oxygens, which is going to beat this carbon down below, which is attached to only one oxygen. And the way we'd work that is we would say that at this point, we would say that's a carbon that's attached to an OOC, whereas down here, this is a carbon that's attached to an OC, an O and then two H's. So it's the comparison of the second oxygen from the double bond to the first hydrogen, whichever one that we want that to be, that allows us to see that we have the 2 priority goes to the circle, and now the 3 priority goes to the triangle. Okay, so kind of breaking this down then as just, I guess what I'm saying is let's let the stereocenter kind of be as simple as possible. We've got 2 on the top, 3 on the bottom, 1 on the right, and 4 on the left. Now, before we connect 1 to 2 to 3, we have to move number 4 off of the horizontal. So pick whichever one you want to swap with. I'm going to swap with 2. So then when we connect, using our green arrow, we go from 1 to 2 to 3, ignoring 4 completely. It's like it's not even there. So that looks like it's counterclockwise, which is S, but we know that we have to take the opposite of whatever we get if we do that little switcheroo trick. And so we get the R configuration. Okay, so the star in our original structure, fructose, has the R assignment. And then we would predict the star in the second one to have the S assignment if this enzyme that this paper is talking about works at flipping that one stereocenter. Well, let's go ahead and do it. We actually know the priorities because the groups are the same. We have 2, we have 3, we have 1, and we have 4. I guess I already labeled the 1. Sorry, I'll just get rid of that. Okay, so just taking that stereocenter away from the complicated structure and just going to a situation where we have 2 on top, 1 on the left, 4 on the right, 3 on the bottom. We once again have a situation where number 4 priority is not on the vertical, or excuse me, is not on the vertical. So we have to switch it with something that is on the vertical. So we're going to temporarily put 4 on the vertical and put 2 on the horizontal. And if we move our green arrow about, that's going to give us a clockwise rotation, which is S. But because we did that switcheroo trick, we have to take the opposite. Excuse me, clockwise is R. Oh my goodness, I'm off to a slow start. I'm very sorry about this. So that's R times -1, which is S, and that matches what we predicted that to be, which was S. Okay, so what I wanted to do was just walk through a quick example. We could actually do this on all of the stereocenters, so which there are 3 on these molecules. There's 1 at the circle, triangle, and star. We could do it at all of them. Maybe that's a worthwhile experience to do. Maybe we save it for the end here. But what I want to focus on is what happens when you've got 2 adjacent stereocenters next to each other for Fischer projections. Okay, so we have Fischer projections with 2 adjacent stereocenters. Calvin, it's good to see you, but I'm recording a lecture. Okay, so go ahead, bud. I'll catch up with you in a second. Okay, so if we have Fischer projections with 2 adjacent stereocenters, we actually just treat this as we analyze it as though we analyze 2 stereocenters or any stereocenters. It's just 2 of them. So we have 2 crosses or 2 intersections. We typically draw this vertically, where the crosses or intersections kind of extend downwards. So what I'm saying is we have this kind of chain propagating downward. Now what I want to do is I'm going to add some groups, like maybe we've got an OH, a Cl, and an H. Okay. So I added some groups to this. Now, what I want to do is convert this into a bond line structure. Hey, Calvin, I'm recording right now. I need you to leave the room, please. So we're going to convert this into bond line structures. So to do that, I need to kind of count up my longest chain of carbon atoms, and that's going to be a guiding light to how we start this bond line structure. So what I've done is I've kind of started from a chain of just a CH3 group that starts as carbon 1, 2, 3, and 4. These numbers are going to get a little confusing, and hopefully the highlights kind of guide our eye. But there's carbons 1, 2, 3, and 4. But because the numbers are going to get in the way, I think I want to erase them. Okay, and just leave the highlights just so we can see where the chain came in. Now we're going to have two stereocenters on this molecule. They're shown in our Fischer projection at the intersection or cross carbons, and we could then match them up to these positions in our bond line structure. And at those stereocenters, we're going to have an OH and a Cl. Okay, so I've got my connectivity, but I need to ask the question, what is the wedge and dash arrangement at the stereocenters? Wedge and dash at these stereocenters. Okay, so I could make this really hard on myself, and I could try to visualize the Fischer projection in the bow tie format that these were originally designed from. But I argued in the last lecture that that's sometimes difficult to do and many times highly unproductive. So what I want to do instead is just take a guess and see if the RS assignment in the Fischer projection matches that of the bond line structure. Okay, so I'm going to take a guess, and by take a guess, it means I'm going to redraw my molecule, and I'm going to add wedges and dashes however I like. I don't care. They could both be dashes. They could both be wedges. I could do wedge dash or dash wedge. It doesn't matter. I personally like to choose having two wedges because then I put my number 4 priority, the hydrogen, and back. It allows me to determine the RS assignment a little bit more quickly. Now, these two structures are the same, and if the RS assignment is the same between them, and if the two structures are the same and have the same RS assignment, then I've really solved the problem of converting my bond line structure, or excuse me, converting my Fischer projection into a bond line structure. Okay, so let's prioritize. So at the first starred carbon, I'm going to give priority 1 to the oxygen, priority 4 to the hydrogen. Now I have a tie of carbon atoms. One is a CH3. Now maybe you're having trouble seeing the CH3. It's just the end of this chain. Okay, the CH3 is certainly going to lose to this carbon and what I call the rest of the Fischer projection or the rest of the chain. So CH3s are kind of nice because they always sort of lose to other carbon atoms. And I can't think of an example where that's not the case. That then gives priority 2 to the carbon I've labeled with a little dot, or the second starred carbon or the second stereocenter, basically just the rest of the chain. Okay, so I have 1, 2, 3, 4. If I look, I see that number 4 is on the vertical, so I can just connect 1 to 2 to 3 to 4. And if I do that, I've got an R configuration or an R assignment. And I don't like where that arrow is coming from, so I'm going to go from the star. So I'm going to label that as an R. I'm just going to double check to make sure it's clockwise. You do this enough time, clockwise and counterclockwise start to flip. Makes you want to buy an analog watch if you had to take this exam in person. Okay, so now down to the second stereocenter, we're going to give the heavy element chlorine priority 1, the hydrogen priority 4, the methyl group priority 3, and the rest of the chain priority 2. It gets a little cumbersome with all these numbers dancing about, but you can get around that by just redrawing the structure bigger if you're interested. Okay, if you notice, I've got number 4 on the horizontal, and it needs to be on the vertical. I like to just switch it with the smaller piece, but you could have switched it with the 2. It's just rewriting a number. So I'm going to switch it with whatever is on the vertical, which is number 3. And then I'm going to go from 1 to 2 to 3, which appears at first glance to be, well, it's certainly true. It is at all glances a counterclockwise arrow, which then makes the stereocenter appear to be S, but we have to remember that we flip 2 of the groups around to put number 4 in back. So we have to multiply this by -1, which equals R. So our original Fischer projection had 2 stereocenters, both of which were assigned R. What we need to do is check our bond line structure to see if that's indeed the case. So if we prioritize, we've already done the priorities, if you recall. 1, 2, 3. This first stereocenter looks really good. 1, 2, 3, and that is R. Now the second one, we have 1, 2, 3. And I have R. So I took a guess and I was right very quickly. Now, one thing that was really helpful is I checked my work by determining the R and S assignment at all of the stereocenters in both of the structures, the one that was provided to me and the one that I provided, excuse me. And so it slows down a little bit, but I mean, if I feel really good about this workflow. I'm not trying to visualize and rotate the molecule around and hope I didn't make a mistake along the way. I'm basically doing one set of priorities for each stereocenter because they work for both structures, and then just making sure I follow the rules when number 4 is or isn't in back and what that means for Fischer projections. But it's kind of a faster way of getting the structures in front of us, and then just checking to make sure that they're right, as opposed to stumbling over what does the Fischer projection actually mean? Because the bow tie structure might be simple enough for some of you to visualize when there's one stereocenter, but as we saw on the first page of the notes, the folks that were writing this journal article are showing multiple stereocenters across several molecules. So, I mean, there's 3 stereocenters in these, and usually that carbon-oxygen double bond is actually another stereocenter. So their Fischer projections are typically best used to depict molecules with multiple adjacent stereocenters, and having a way to quickly determine the RS assignment in all of them and correlate that to a bond line structure is important. Okay, so that was us practicing going from a Fischer projection to a bond line structure. Let's see if we can go from a bond line structure to a Fischer projection. So I like to draw straight chain molecules. If you go for rings and that sort of thing, you're really making it hard on yourself. So we're going to pick on straight chain molecules. Let's go ahead and let's do 3 stereocenters. Why not? And let's make them all wedges. The purpose of this lecture isn't to test your ability to, the purpose of this lecture is Fischer projections. So let's make it easy on ourselves, make them all wedges. That allows us to determine the RS assignment fairly seamlessly on the bond line structure. Okay. So we have, maybe I'll use different symbols. Maybe that was a little unclear last time. So star, triangle, circle. Okay, so we have 3 stereocenters, which means we need to have sort of 3 crosses or intersections in our Fischer projection. And we'll let the top one be star, then triangle, and then circle. So all of these intersections represent a carbon atom that's a stereocenter. Now the starred carbon atom has attached to it bromine, hydrogen, and CH3. Let's go ahead and put hydrogen as a vertical substituent, make it easy. CH3 over here and bromine over here. Now wait, Willoughby, why did you put the bromine on the left and the CH3 on the right, and why is hydrogen on the top? This is exactly the same workflow that I did for the bond line structure drawing. So when I wanted to convert from a Fischer projection to a bond line structure, I made sure I had the connectivity correct, and I took a guess and then just determined R and S at all of the stereocenters. If I'm wrong, I'm going to flip it over. If I'm right, or if they match, I'm going to, let me say that again. If the RS assignment doesn't match between the Fischer projection and the bond line structure, I'm going to assume that I was wrong. No big deal. If I know I'm wrong, just change the answer and you can recheck it if you want. So I'm just taking a guess here. I just want to quickly get a Fischer projection with the same connectivity as my bond line structure in front of me, then I'll worry about making sure that the stereochemistry is the same or the RS assignment is the same. Okay, because I can flip things around once everything is connected properly. Okay, so on the next stereocenter, the triangle, we have fluorine and hydrogen, along with the rest of the chain going one way and the rest of the chain going another way. I'm just going to go here and here. And I know I've got hydrogen on the horizontal. I'll just have to deal with that when I determine the RS assignment. Now, for the chlorine, I have hydrogen. So I can put that on the vertical because that makes my life a little bit easier. I don't have to remember to flip the RS assignment around. So put hydrogen on the vertical, then sure, I'll put CH3 on the right and then Cl on the left. And if you're having trouble drawing the CH3s, I'll write those in at this point. They're just the end caps of our chain. And if you want to see the chain, I start one carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons matches 1, 2, 3, 4, 5. So there's me navigating around my chain. Okay, so what I want to do is determine R and S at all of the stereocenters for both of these structures, make sure that they're the same. If they're not the same, I need to flip the stereocenters or flip the kind of arrangement in my Fischer projection. So let's go through it. So for star, we've got 1 going to bromine, 2 goes to the rest of our chain because CH3 usually gets the lowest priority for carbon substituents, and then 4 is in back because I set myself up to make that easy. And if I look, 1 to 2 to 3 is clockwise, so that is R. And I didn't have to do any flipping because I set it up so that hydrogen was in the back. So this first stereocenter should be, if it's R in the bond line structure, it needs to be R in the Fischer projection that I provided. So I go 1 here, 2 here, 3 here, 4 is on the horizontal. This isn't looking good, right? What are we going to do? It's counterclockwise, which means that we have drawn the S stereocenter. We're going to lose all the points. Well, no. What we do then is, if you have an eraser, you should use the eraser. I'm just making a point. We're just going to swap 2 of the groups. If the CH3 is on the left and the BR is on the right, then all of a sudden, I have to switch my 1 and my 3 around. I'm at 1 and I'm at 3. And then my arrow no longer goes counterclockwise for S, rather it goes 1 to 2 to 3, which is R, and it matches. And maybe I should redraw this if I don't have a pencil, and I will at the end. So BR on the right, CH3 on the left, and H on the top gives us an R assignment for the first or starred stereocenter. So far we match. Now let's go down back to our bond line structure. So 1 for hydrogen, okay, or for fluorine, 4 for hydrogen, excuse me. Now we have a tie. And it's not a trivial tie between carbon star and carbon circle. Both are carbons, both have CH3s attached, both have H's, but we first compare the highest priority element attached to each carbon. So if I draw C star and C circle, I've got Br, then C, then H, versus Cl, then C, then H at C dot. So it's a comparison between the BR and the CL that's going to allow us to see the difference between C star and C circle and how we prioritize them for these triangle stereocenter. A lot of shapes. Okay, so C star gets the highest priority. If you get out your periodic tables, you'll see that bromine has a higher atomic mass and wins the day in terms of priority over chlorine. So we have 1, oh, goodness. No, we have 2. Priority 2 goes to the star, and priority 3 goes to the circle. If we connect our arrow, we put number 4 in back by design, then that looks to be R. So we're at R for the middle stereocenter as well. Now 1 to 2 to 3 to 4. Okay, so for me to get this, I have to put the number 4 on the vertical. I am picking about the hardest example possible. Okay, so I'm going to switch number 4 with number 3. It could have been number 2. You will get the same answer in that if you connect 1 to 2 to 3, 1 to 2 to 3, that's a clockwise arrow, which is R, but we have to multiply it by the opposite, which is S. Okay, shoot. So they don't match. What do I do? Well, when they don't match, I'm going to pick a different color. You cross them out and replace them with the group on the other side. I'm just going to flip the sides around, and I can prove to myself that that then becomes the R configuration. So I took a guess, and so far I'm 0 for 2. I'm going to have to do a lot of rewriting here, but notice I didn't have to bust out the bow tie structure and start to rotate molecules around. If you want to do that, if you're better at that, that's okay. You just have to get the right answer and show your work to kind of demonstrate to me how you know it's the right answer. But if you do that, it'll be fine. I don't want to discourage people from rotating molecules around in their mind. Okay, the last stereocenter should not be as challenging, but I don't know if I got it right. 1 to 2, 3, 4. I prioritize chlorine as number 1 because it beats carbon. Then between the two carbon atoms, CH3 is always a lower priority than any other carbon substituent. So that gets the 3 priority over 4, which is goes to hydrogen. And the 2 priority goes to the rest of the chain. So 1 to 2 to 3. This looks to be S, right? Okay, so I just want to make sure it was indeed S. Now, if we go over here and do the exact same priorities, so chlorine, I think I was making chlorine with 1, rest of the chain with 2, CH3. Oh my gosh, I went 0 for 3 on my guess. So 1 to 2 to 3, that's R, and I have to leave that put. We don't flip that one because H is on the vertical. So what I want to do then is flip 2 of the substituents again. I'm just going to put the CH3 on the left this time and the Cl on the right. Okay, so the correct answer, and by that I mean an answer where the connectivity and the RS assignment matches both, is one where in this depiction, I have the halogens, the Br, the F, and the Cl all on the right of my Fischer projections, the hydrogens on top and bottom, the methyl groups on the left, and in the middle we have a hydrogen pointing on the left. That should give us R at every, that should give us R at the first 2 stereocenters and then S at the bottom stereocenter. And I'm just doing a quick check, and it looks like that is the case. Okay, so we got it wrong, but it's okay, because when we have it wrong and we know we have it wrong and we find out that we have it wrong before we submit it to Willoughby for grading, all we have to do is flip our stereocenters around, determine R and S. I think the hardest thing in determining R and S is making sure you get the priorities correctly, and then after that it's just connecting 1, 2, 3. Is it counterclockwise? Is it clockwise? Was number 4 in back? So do we have to flip it? That sort of thing. So, once you do the priorities, it's kind of set up for you to finish. And that's why I really like the guess strategy, because you only have to prioritize once, even though you're making multiple RS assignments. You only prioritize once because the priorities are the same between those 2 structures, because you made sure that they have the same connectivity. So at that point, I'm going to stop with Fischer projections. It was kind of a quick aside, but an important aside in our discussion of stereochemistry. And we're going to go on to some more general topics related to chirality and stereochemistry in the next few lectures. But don't let this go, because you'll be missing a big part of the field, which is carbohydrate chemistry. And as you could see from this lecture and the last lecture, when I actually provided these examples of Fischer projections being drawn for the community at large, carbohydrate chemists and carbohydrate scientists really prefer to draw Fischer projections as, or carbohydrates, excuse me, as Fischer projections. And these ever increasingly important molecules, for these ever increasingly important molecules, it's necessary for us to be able to kind of communicate to each other by way of this more arcane like depiction of molecules, which are Fischer projections.